Hello, everyone. Thank you very much for coming. My name is Ofek Shilon. I'm a developer at an HFT firm called Eastar Research, based in Israel. I'm available by the handle Ofek Shilon at all major platforms. And I will be presenting today a little-known tool, mostly in the LLVM universe, called optimization remarks. Now, what are Clang optimization remarks? Optimization passes typically leave behind some logs. Now, admittedly, these logs were phrased by and intended for compiler authors. So more often than not, understanding them requires quite a bit of deciphering effort. But once this effort is undertaken, they can sometimes be a goldmine for optimization-aware developers. I mean, this is no longer some vague warnings about pitfalls, like beware of aliasing. It can degrade your optimization. These are exact pointers to which optimizations were prevented by aliasing concerns, for example, and where. So I aim that by the end of this talk, you would all know how to obtain optimization remarks, how to interpret some of them, and how to use that understanding to do something about missed optimizations when you come across them. The first 60% of the talk would be restricted to the Clang universe, but we will broaden our scope beyond that later. So, how do we get optimization remark? The oldest such tool has been around for quite a while, and it's a humble compiler switch, rpass. R probably stands for remarks, I don't know. This dumps the optimization pass logs, aka optimization remarks, to std out, and it looks something like this. This is the kind of display that makes my eyes glaze over. It's a wall of text without structure or context or grouping, and we should be able to do better. Now, the first step towards better is something called LLVM opt report, which looks something like this. This is better. This is a textual display of the compiled sources alongside this column here, which encodes, encrypts is a better word, which encrypts approximately what happened and where. Optimization remarks. This tool is alive, it is documented. Please don't use it. We have better things today. A major step forward is this tool, opt viewer. Its output looks something like this. This is an HTML of the compiled sources alongside optimization remarks as annotations interleaved in place among the source lines with a full text, with links to other locations within the source where applicable, and with other various goodies that we'll at least touch upon soon. This work is from 2016. It was led by Adam Nemeth from Apple. I do wholeheartedly recommend watching his talk in the link here. It's a brilliant one. This tool is today part of the LLVM master. If you ever cloned LLVM, you already have it. If you didn't, or you prefer not to, you can obtain it via a download of a deb package. The most basic way to obtain such nice HTMLs of sources with annotations of optimization remarks is as follows. Add to your build script, whichever it may be, a single switch, fsave optimization record. Once you do, YAML files, opt-YAML files are generated alongside your obj files. Here's a snippet from such a YAML file. Clearly, it's meant for consumption by a machine and not by a person, and this consumption is a Python script called optviewer. Optviewer py, you run it and you tell it where to generate the HTMLs, where to take the sources from, and where to obtain the YAMLs that were produced by the previous compiler switch, by the fsave optimization record. So, the large majority of the talk would be dedicated to understanding these orange intertwined lines, but let's take a minute to discuss other goodies that are present in this view. First, these numbers on the left column, these are hotness numbers. If by any chance you have the good fortune of being able to build with PGO, you have some hotness data. And optviewer is smart enough to incorporate this data and display it here alongside the source lines, thereby helping you prioritize what's important and what not so much. Next, this column here on the right, it's an inlining context. Every function can, and typically does, undergo inlining into various different colors. Once it does, different optimization decisions can be taken and are being taken by the optimization passes, and so different optimization remarks are emitted. Here, for the first time, you're able to view the optimization remark within its inlining context. Last but not least, this half a line. Load of type i32 not eliminated in favor of store. This text as is was available since forever in RPass. Adam Nimet's work added this half because it is clobbered by store. I realize both halves are still opaque, but we will dive in great detail, and this part contains a great deal of info. Okay, now there is a more advanced version called optview 2, which I will not go into detail about, but I will dedicate 1.5 slides to it. Optview is great, but it is heavy to the point of being unpleasant to work with. Runs on medium to large size projects. I had to stop after it consumed maybe 100 gigs of RAM, and even if I was able to run it, it produced HTMLs in sizes that break browsers. And even if I was able to jump through all these hoops, what I was left with is a dump of tons of info. Most of it was noise to me. So for the past year or so, I have been hacking away at these scripts, trying to adapt them better for my personal needs and hopefully for other general dev audience. I collect only optimization failures. I exclude system headers. I might be giving up some actionable info there, but for the most part, I'm not. I remove a ton of duplicities. I now have the ability to filter via regexes on remark types and text. I can split to subfolders. That's actually a big deal. That's what makes running on medium or large sized projects feasible. There's other stuff going on, not only by me, with help from friends and colleagues too. And the reason I won't be discussing it in great detail is because it is now in the process of being merged to LLVM's trunk. So if by chance you're watching this from 2023 or beyond, this repo should be dead. If you want to try out these tools in the near month or so, please go to this repo. And most of what I'll be presenting will be taken from there. And as a final goodie, most of optviewer's capabilities are today available in Compiler Explorer and have been for quite some time. if you go to Compiler Explorer and pick any Clang flavor, you could add new optimization panel. Once you do, you'd get something like this. This doesn't have interleaved optimization remarks, but it does have this colorful sidebar. And once you hover above it, you get the real optimization remark text. Most of the remaining slides will be screenshots from Godbolt, examining some toy snippets of code to try and understand optimization remarks. Let's go ahead. Let's start with a simple one, inlining. This is not a Godbolt screenshot. This is a screenshot from an analysis of some OpenCV source. Okay. The structure of mat will not be inlined into wherever because its definition is unavailable. That should be easy. What does that mean? Does anyone have a guess? Okay, it means that the destructor of mat had only its declaration available in the header, as headers typically do. Now, if I were an OpenCV developer, I might have been surprised because the destructor of mat is simple enough to at least be considered for inlining. And since the compiler had no visibility into it, the implementation was not inline, was not included in the header, the compiler couldn't even consider it. Now, even had the implementation being included in the header, that still doesn't promise the function would be inlined. Take a look at the comment below. Function yada yada not inlined into yada 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 because too costly to inline. That's a different reason. The compiler performs some heuristic approximation of the cost in code bloat for inlining, compares it against some threshold, and in this case and some others, decides not to inline. Now, this might be the right thing to do. Judgment needs to be exercised here, but suppose I was unhappy with this optimization decision. Does anyone have an idea what I might be able to do about it? Sorry? Change the threshold. That's an excellent choice. At least in GCC and Clang, there are switches to change it. This is typically project-wide or at least file-wide setting. Maybe there's another idea what I can do about this specific function. Force inline. That was exactly the second thing I was about to suggest. Thank you very much. Okay, let's go into something more interesting. Clobbered by store. I have a function here with a silly loop inside. This function takes a buffer of 10 ints in A and some desired increment in B. Function iterates over the 10 A slots and adds B to each one. Now, if for some weird, whatever reason, someone would have asked me to generate assembly for this function manually, what I would have done is store B in a register, iterate over the 10 slots of A, and add B to each one. This is not what the compiler does. By the way, this talk would be assembly heavy. Don't worry about it. Even if you're not comfortable with assembly, there's no reason you shouldn't get the gist of all the ideas here. The main idea is you don't have to dive into disassembly to understand optimizations. So the compiler loads B from its memory address into the register EAX, and then uses EAX to increment A0. Loads B again from memory to EAX and uses it to increment A1. Again, loads from memory and increments A2, etc., etc. Now I'm guessing most of you already know what's going on, but let's pretend we don't. And let's go to optimization remark for clues. Let's hover above this red rectangle and see this. An optimization was missed. A load of type I32 was not eliminated. Either compiler wanted to eliminate the load of type I32, that's B. And by load, when compilers say load, they mean load from memory into a register. But either compiler couldn't do it. Why not? Because it is clobbered by store. As of today, we even have a column marker. We know the location within the line. The store into AI clobbers B. Now, at this point, everyone should understand what's going on. There's a name for this phenomena, and it was mentioned in at least 2 talks just today. What's the name of this phenomena? Aliasing. Thank you very much. The compiler is protecting against the scenario that B was passed in as a reference to one of the A elements. If it did, if B was a reference to A3, then after the 4th iteration, the increment would be changed and would have to be loaded from memory again. Okay, now there are simple things to be done about it. The simplest being decorate with restrict. Restrict is a way to communicate to the compiler that the memory populated by A does not alias with any other name within scope. Once we do, the optimization remark vanishes, and the generated code is substantially better. In this particular case, the optimization that was inhibited by aliasing concern was a vectorization, but actually that doesn't matter for my point. Now, take a look at something a bit more interesting. Here's the original source and the original generated assembly. Now let me take a small, seemingly meaningless change. Let me change int to long. The optimization remark is gone, and this is not a fluke. The generated code is better. Now this is a slightly more exotic C++ phenomena. Don't feel bad if you don't know about it. This is called, I'm sorry, did someone say the name? Strict aliasing. Thank you very much. This is strict aliasing in action. Don't feel bad if you've never heard about it. Strict aliasing, originally I had here a slide with standards, but it is utterly incomprehensible to me. Let's speak human. Strict aliasing is a permission we give the compiler to assume that objects of different types do not alias. This is what we saw in action in last slide. And this might be useful. This could have been a way to communicate our knowledge of non-aliasing to the compiler. You should know that restrict, as of today, has rather limited usage. It is accepted everywhere, but has actual impact only when it decorates function arguments. Strict aliasing does not suffer from this limitation. And this should have worked, but in practice it doesn't. I submitted several LLVM issues. This is a link to one. I won't go into further details here. You are very welcome to click and join the conversation. Okay, just a second. Are there any questions up until now about aliasing? Yes, go ahead.
So why does the compiler or can't the compiler assume that you're...
I'm sorry, I'm having a hard time hearing. Can you please step up to the mic? Thank you.
In your example, right, it was constant reference B. So technically, right, I'm not allowed to write to B. because it's supposed to be const. Why is the compiler not allowed to assume that this thing doesn't change, which means it shouldn't be able to alias with the ints of A?
That's a common misconception. Thank you for bringing that up. That's not what const does. Const says that you cannot modify B's context by using the name B. It says nothing about indirect access through other names. Thank you for that. It needs to be said also, in case it isn't obvious, if B wasn't passed by reference, none of this would have been a concern. Another trivial thing that we could do is copy B into a local, and then all aliasing concerns are off. Okay, let's move forward to something even more interesting. Clobbered by call. I have another silly function here. It's called f. It accepts an int I, calls some func I, the signatures are up here, and then increments I calls whatever, increments I calls whatever, increments I and calls whatever. Again, if some sadistic warden from math riddles would have forced me to generate assembly manually for this code, the first thing I would do would be probably to coalesce these 3 increments of I into 1 increment by 3. And on second glance, I'd probably eliminate I altogether. It is entirely unused after the call to some func. Again, this is not what the compiler does. The compiler not only does not eliminate I, but does increment it 3 separate times. Now, this is a less famous phenomenon, so I imagine less of you know what's going on here. So let's go to optimization remarks for clues. When I hover here, I see missed, load of type I32 not eliminated in favor of store because it is clobbered by call. The phrasing is similar, but the underlying phenomena is very, very different. Observe that some func takes its argument by reference. So during this call, the address of I is available within some func. The technical term for this is that pointer escape had happened. Once the address of I had escaped, all sorts of crazy things can happen. Some func can store it in some global location or some member. Even worse, whatever could access that member. Its behavior, its return address, might depend on the value of I. And so to preserve the semantics as listed in the code here, I needs to be incremented separately. There's no way around it. This sounds crazy, but the compiler has no visibility into these implementations and so cannot rule out this behavior. But we are in compiler land. Common sense has no power here. All crazy things can happen. So, I can suggest, in fact, quite a few ways to try and counter these missed optimizations. First one is attribute pure. Attribute pure is a way to communicate to the compiler that some func does not modify global state. That is, the first event in the chain of events that the compiler defended against does not happen. Even the escaped address of I isn't stored anywhere. And indeed, the generated code is much, much better. However, this is slightly cheating. If some func does not modify global state and returns nothing, it essentially does nothing. It has no observable side effects. The compiler is able to make that reasoning, and note that it eliminates the call to some func altogether. So attribute pure is a tool to keep in mind, but in this particular example, it probably didn't do what I meant it to do. Here's another nice tool, attribute const. Attribute const poses a stricter restriction on the decorated function. It means that whatever not only does not modify global state, it doesn't even read it. It can't even access it. So even if the escaped address of I is stored somewhere global, it cannot impact the behavior of whatever. Indeed, the generated code is better. The call to SumFunc is maintained, but note that only a single call to whatever is made. If whatever takes no arguments and does not depend on any external state, there's absolutely no reason to call it 3 times. All 3 times must result in the same return value, and the compiler is smart enough to make this deduction. It calls whatever once and copies the return value into the 3 res slots. So again, this might or might not be what you meant, but there is a still better tool that best captures the semantics that I intended to convey. It is attribute no escape. Note this is not an attribute of a function, it is an attribute of an argument, and it says exactly what its name implies. The address of this argument does not escape through this call. The generated code is exactly what I would have assembled manually. And all 3 tools are good to keep in mind. They are all useful in various different contexts. Now here's another surprising tidbit. Here's a surprising way to stop the optimization remark. Instead of I typed +I. Anyone has an idea what happened here? That's right. It seems the semantics are not changed, but in fact they are. +I is now a temporary object. Even if its address escaped through the call to SumFunc, it is no longer the address of I. And modifications to I do not impact this escaped address. And optimizations are free to apply. Okay, the last thing I want to say in this, on this optimization remark is that sometimes the offending code is not your own. Here I replaced the call to SumFunc with a call to OFStream out operator. And the same optimization remark and the same inhibited optimizations appear. Now, I actually had a chat with Marshall Claude this morning. No, sorry, yesterday. And as far as we know, this wasn't even ever considered, so it might be worth looking into, but that is still not the case. Okay, just a second. Questions so far? Yes.
In that example, previous slide, would that, if that function were subjected to link time optimization and the definition of SumFunc were visible there, would that have been further? Would that have been re-optimized?
Great question, thank you. The answer is a definite sometimes. No, I actually intended to discuss LTO in quite some detail. I'm not sure I'd have the time now, but I am, let me say this, I'm often unpleasantly surprised by LTO's added value. A lot of extra analysis is theoretically available if you build with LTO. A lot of aliasing concerns or escape concerns theoretically can be eliminated. The compiler at the LTO phase has enough information to address them, but it typically does not. If we'll have time, we'll go into it in some detail. Okay, the final example of an optimization remark that I want to survey in detail is this. Fail to move load with loop invariant address. Here I have a class, finally. This is a C++ conference, and there were no classes yet in this presentation. With some bool and some method, I loop 5 times, check mcond, and call f. Now again, if I were a human compiler, I would hoist the check of mcond outside the loop. I would check mcond once and then either call f 5 times or do nothing and return. This is not what the compiler does. The compiler checks mcond and calls f 5 separate times. And now we have a tool to stop the guesswork and try to get some clue into why. Yes, question?
No, I was guessing.
Go ahead, guess. But please at the mic so everyone could listen.
F might be able to modify mcond when it's called.
Please stay there. How can that be? F takes no arguments and is not even a class method. How could it modify C's member?
If it had like a pointer to an instance of C.
Thank you, you're right. Oh. I should have started from this, you're right. Don't worry. Let it be said, when you're working within classes, the battle against pointer escape is a lost battle. Not only is the this pointer accessible in all class methods, the this pointer of the particular instance you're running on might be stored anywhere in the program memory. The compiler cannot rule out this possibility, and so it cannot rule out the possibility that F modifies mcond. Yes? Thank you.
Could you please tell how F could theoretically modify mcond if it's private?
Yes.
Friend? Maybe a friend, right?
I'm actually giving a lightning talk about a very similar subject tomorrow evening. I think I have here something that could clarify something similar. What most people are worried about is constness in this regard. Both private and const do not guarantee anything as far as the compiler is concerned. There are legal C++ ways to modify both. Here's an example of one. It is very improbable, but it can happen. If we'll have more time, I'll show more examples of this type of behavior. Okay, so as a matter of fact, you already have tools at your disposal that can do something about it. I'm sorry, another question?
Yes, on the previous slides, you showed two different warnings, cobbled by call and cobbled by invoke. I did not understand the difference.
It's really not important. Invoke is the term used by Clang for functions that can throw. That's it. So, actually decorating F as const would have sufficed, but I want to take this opportunity to add another tool to your arsenal, saying that if the compiler is unable to hoist the member by itself, perhaps I can. I can. Once I do, the optimization remark vanishes and the generated code is as you would expect. Please note, this is not good C++ code. Please don't go copying members to locals to improve optimizations unless you have a very concrete reason to do so and you see a measurable impact. Okay. For reference, I concentrated the 4 examples we surveyed here. Clobbered by store is a telltale sign of aliasing. Clobbered by load, it's a mistake, it's a typo. Clobbered by call is a sign of escape, as typically is failed to move load loop invariant. And when you, let it be said that when you inspect compiler optimization at this level of detail, more often than you'd expect, you come across missed optimizations that truly have no semantic justification. These, more often than I'm comfortable admitting, these are true compiler limitations. I have opened a few LLVM issues about it, but so far they haven't gotten lots of attention. Okay, we have time to discuss at least some aspects of other build configurations. LTO build was already mentioned. I'll go over this briefly. In a regular build, optimizations are performed at the compile step, and turning on the switch fsave optimization record indeed calls these compilation steps to emit optimization remarks for us to analyze later. In LTO builds, the compilation step does not perform any optimizations, or very rough ones. The optimizations are performed by the link step. Now, this causes some very confusing results because turning on the fsave optimization record switch causes these compilation steps to emit optimization remarks, and they can be mighty confusing. You're bombarded with could not inline because had no definition remarks, which are clearly bogus. And these build steps are silent. So after some effort, I was able to devise some hacks that enable getting optimization remarks from the link phase of LTO. I'm dumping them here for completeness. It's essentially it's the use of a different tool, LLVM LTO, that is very close to being undocumented, and it is included in LLVM distributions. It is very hard to work with. There is no parallelization. There is no parallelism. It is a single processing of a gargantuan file. And I had no luck getting new information from there. In my personal experience, you'd get very similar mileage if you'd inspect optimization remarks of regular builds, and whichever improvements you'd be able to apply there would add value to LTO builds. I don't dare say anything categorical. This is my own personal experience. Okay. Now, let's turn our eyes to different compilers and maybe even different languages. 2 years after this work, in 2018, David Malcolm, who's a GCC developer working from Red Hat, put together a similar prototype in GCC. GCC to this day accepts an F-save optimization record switch. This did not make it into the GCC trunk. To process the generated remarks, you need scripts that are present in David Malcolm's personal repository. These are not YAML files, these are JSON files. The information is hierarchical. There are various other subtle differences. And here is a screenshot of a snippet of such an output. And I won't go into this in any more detail because it is essentially dead since 2018, and I actually wasn't able to get meaningful results from it. Even if you are able to complete a run of the compiler with the switch, you typically won't be able to complete a run of the processing script. I think this is great work with lots of potential, and I do hope to see it revived, but this is not the case currently. Now, I did show the mitigation tools only in Clang, but other compilers have very similar ones. GCC has restrict, pure, and const. Intel's compiler has restrict and const. MSVC also has restrict and const in other vocabulary and slightly different semantics. If you want to apply these conclusions to MSVC, please read the docs before doing so. And it needs to be said that in comparison to LLVM, the other compilers have rather primitive diagnosis tools. They don't have real optimization remarks, but the conclusions that you draw from analyzing your code, even just snippets, on Clang typically hold to other compilers. This is not categorical. This is a rule of thumb that's based on lots of experiments. All compilers struggle with aliasing. All compilers struggle with pointer escape. You're able to analyze it well in Clang, but all compilers could use extra info in those places. If you're working in a cross-compiler setting, you'd probably want to apply these attributes wrapped in some compiler-sensitive macro. A good starting point is a project called Headley. It's a single header, contains essentially a bunch of macros like this. If you do, please note whether this limitation still holds. Okay, we have a bit of time to discuss some cousin languages. Rust carries some good news about alias analysis. This is not Rust code, this is C code. This is the toy code that I used to demonstrate aliasing remarks. This is the same code expressed in Rust, and without any decorations or exotic subtleties, this same code generates the optimized assembly. The reason is that Rust comes out of the box with anti-aliasing machinery. Rust's borrow checker means that you'd have to jump through various hoops and write some unsafe code to be able to generate aliasing in the first place. And, well, this is September 2022. You can't really have a C++ conference without mentioning Carbon. Carbon will probably carry some good news about pointer escape. This is a C++ code that I used to demonstrate escape analysis. This is the same code expressed in Carbon. And note that in Carbon, you don't have to prefix the argument I with var. If you do prefix I with var, it means I is a variable. You can, for instance, take its address. If you don't prefix I with var, I may not have an address. It is not a variable. It could be passed in a register. And if this is your signature of some func, pointer escape cannot happen. There is still no Carbon complete compiler to demonstrate these results with, but this is a very reasonable thing to hope. Okay, a reasonable question that typically arises is this effort worth it? The short answer is, I don't know. I can give you some data points. First, there's a growing body of academic work within the LLVM developer community that strives to, how should I put it, to justify further investment in internal attribute machinery. And these are all three works I highly recommend to read or watch. These are brilliant works, most led by Johannes Dorfert. They arrive at rather different conclusions. Petospa showed 50 to 20% speed up using attributes that are not all available in C++. These are internal IR attributes. Oracle, which was a work that focused on alias queries alone, showed no impact. And HTO is a header time optimization. I still have hope that this would be merged to trunk someday. Showed through extended attributes alone in C++. They describe it a gain of 50% of LTO without LTO. These are hypothetical ceilings of what you might be able to hope to achieve with a careful application of these attributes. And I can tell another data point is my own personal experience. In my own work, I used similar trickery to attack a function that was a known bottleneck that took 6 microseconds. And after we gave it some optimization remarks love, it was reduced by 25%, which was a nice win. This was a known bottleneck, and it received some optimization love, and yet we were able to reduce it further. So the closest thing I have to recommendations is concentrate on known bottleneck. You'd get many tens of thousands of optimization remarks if you were to scan your project with these tools. Look first where you know it matters. And in particular, if you work at sub-millisecond scale or in very, very tight loops, the risk that you'd waste your time and effort is minimal. I can pretty much guarantee that you'd see measurable impact. Okay, final thing, I want to say that this might be the start of a new approach. I hope it can be developed further. We're not used to having a conversation with the compiler. We're used to having a monologue, like writing our code, dumping it in the compiler, running away and hope for the best. This doesn't have to be the case. The compiler, as you can see, can talk to you. It can ask you questions. If you acquired the skill, you can understand the questions and answer. Not always. I showed 4 examples. There are about 20 more optimization remark categories today as of Clang 14. And still, most of them were non-actionable to me. And the last thing I want to say is I want to say thank you to friends and colleagues who took part in this work. Ilan Ben Chagai, Oded Sharon, Gal Falcon, Roy Barkan, and Lior Solodkin all helped put this together, either through PRs or discussions or deciphering optimization remark riddles that I wasn't able to myself. Thank you very much, and I'll be very glad to try and answer questions if you have any.
I have a question from online. It says, why does the standard still allow for modification for constant variables in such non-obvious ways, apart from backward compatibility?
Why is the standard what?
Why does the standard allow for modification of constant variables in non-obvious ways?
You're referring to the out-of-band slide that I showed?
I assume so.
It tries not to, but developers apparently are more devious than committee members. Now, this is essential. I think of this as a loophole in the standard. I don't think of it as a deliberate decision. By the way, if this function would have been decorated with attribute const and not just C++ const, compilation, well, actually I should test it, but it should have failed. Or at least this code would no longer be defined behavior. Yes, go ahead.
I have a question about const reference modification. You said it's only a guarantee that that variable cannot be changed by its name. But if it's true, if we do not use any const cast, and the compiler still assumes that it can be modified, then creating any car pointer would kill any optimizations because the car pointer basically could point to anything. Is that correct? What I'm saying, yeah, sorry. Basically, what I'm asking is, if I create a car pointer inside my function, compiler may assume it points to any local or global variable, const or non-const. And then it should basically do not optimize any of these variables.
Well, do not optimize any of this is too harsh of a statement, but yes, that is true. Many optimizations are inhibited in the presence of pointers that the compiler is unable to reason about. That is entirely true. That is my experience. Sorry, could you repeat this to the microphone?
Type punning is still illegal. So what you
It's
said
true.
about
It's
what
true.
you said about
He was
aliasing-
asking about a char pointer specifically.
But like you cannot go from long to char to int star.
That's true.
So
That's
it still doesn't blow a hole like a global hole. The aliasing will still apply.
I imagine that this was the historical motivation for strict aliasing, to allow some sort of optimization.
Yeah. So
We would be crippled beyond use without it.
I have a comment which actually bears on this, but it would be easier to point out in the slide where the pointer escape happens.
Give me a second.
With the sum function and whatever. Yeah. That one.
Yes.
So there is actually something more subtle going on here, which may be good for somebody, because somebody may have a question I would like to point out. So nominally, some func should not be able to modify I through the argument because it's a constant ref, and you shouldn't be able to cast constants ref to a non-const int star, which would be a global pointer.
It would be UB, that's right.
Except you can, casting away const is not UB unless the object was created const.
That's true.
So if you made the parameter const int,
Yes.
then technically the compiler should be able to make it optimization. I don't know of any compiler that actually does, but then technically it would be UB. And it bears on that question that was asked online. Const in C++ means a lot of different things. It seems like what they were asking is, how do I declare an object itself to be immutable? You created const. Theoretically, it means it's immutable. Most compilers don't pay enough attention.
I think, thank you for that. Let me make 2 comments about that. I still have time? I still have time. First, I did consider, actually the first version did have const int here, but I opted to demonstrate the escape through increments to I, so this was out of the question. Now, there actually some cases were present at previous CppCon talks. There are cases where the compiler unjustifiably ignores const, but in my experience, most of the time, I can come up with devious constructs like this that can, through legal C++, modify const variables. My mental image is that sometimes along the way, compiler writers just gave up and decided considering const was just not worth the effort. Please come to the lightning talks tomorrow. I can show an example where it is. Where if it was created const, you're able to modify it. Please to the microphone.
I believe the point here is if it was created as a const, then you can modify means you just found an undefined behavior. Because most probably it will just throw some kind of hardware exception or something like that.
I disagree. I think I have legal C++ that does it, but this is not the point of this talk. Let's discuss this further tomorrow. And I might learn something new. Maybe I did trigger UB in some indirect way that I wasn't aware of. Any more questions? Okay, guys, you're very welcome to give this tool a try. Please tell me if it works for you, and even more importantly, tell me if it didn't. This is still work in progress, and I'd be very happy to take suggestions and even pull requests. Thank you very much.